Hi everyone. So in this video, I'm going to kind of talk us through the reaction at the beginning, including some tips and tricks, if you will, of doing the reaction. And then what I'm going to do is go over some of the more practical details, like how to find the limiting reagent, how to write the mechanism, and how to do the separation scheme. So that's kind of, the plan of this video. And you're kind of going to be a little bit left on your own at this point to do the hypothesis based on some of the things that we talk about in the other sections. So that's kind of where we're going here. So first thing, let's look at the actual reaction. So we're going to do an elimination reaction of cyclohexanol using a sulfuric acid catalyst, which is regenerated during the reaction, and we're going to form cyclohexene. And there's a few practical things to note here. The first thing is we're going to use a strong acid, so you need to be mindful of the safety hazards of using a strong acid. The other thing is we are going to use a distillation apparatus, and there are some safety hazards of using a distillation apparatus as well, because you never want to open up the hot side of this while it's still hot. So you do need to let this cool down before you take it apart. You can take off the receiving flask and move on to the next step, but do let this cool down before you try to take it apart. We're also going to talk about how the fact that this is a reversible reaction plays a role. We're going to talk about the amounts of things that we're going to use, and so on and so forth. So I'd like to thank Katie for this because I watched her do this on last Friday, and that is helping me out a lot because there are a lot of practical details here, just based on the complex nature of how this is all set up and things like that. So just make sure you're familiar with how to set up a fractional distillation apparatus before you come to lab, because you don't want to spend a long time doing this, setting this all up, because you want to get the reaction moving along. There's quite a lot of work to do, and as always, we encourage you guys to divide and conquer. All right, so divide up the work between you and your lab partner, and you can get it done a little bit quicker. All right, so let's go ahead and talk about this. So what we're going to do is we're going to use 10 milliliters of cyclohexanol, and we're going to add to that 6 milliliters of 7.5 molar sulfuric acid. And then we're going to heat this, as we said before. Now, it's really important that we don't overheat this. So if you have a heating mantle with a temperature controller built into it, you're going to want to use about 25% of the range. So said another way, from all the way off, turn it up about a quarter of the way. All right. If you're using a variac, which is the separate box that the heating mantle plugs into, you want to use about 35% of the range. Again, from all the way off to about 35% up of the way up. All right. Remember that it does take time for this to heat up. So if you don't see it heating in the first 2 minutes, that's not a huge deal. And don't worry about that. Just give it more time. You can burn this, so the reaction mixture will turn black. If that happens, you can continue to do the reaction, and you can isolate some product. This happened during testing, and it wasn't a huge problem. However, it does make it a pain to clean it up, and it's not good technique. So let's keep the heat low, and let's get a good reaction to go. The other thing that's important to note is you are going to need to insulate all of this fractionating column with some aluminum foil, because if you don't, it's going to take forever for this thing to heat up all the way, if it even will heat up all the way. So basically, just make sure you insulate all the way up to up to this, so that your product can actually fall down into the receiving flask. So those are just some practical notes. So again, 10 milliliters of cyclohexanol and 6 milliliters of 7.5 molar sulfuric acid, and the sulfuric acid is a catalyst, so you would not want to count that as the limiting reagent. The other thing to note is we are going to put some boiling stones in here, so we're not going to use stirring this time. We're going to use boiling stones instead. So you want to put 3 to 5 boiling stones in here. That just helps prevent bumping, which is very important. So basically it bumps, it boils and it pops up into the fractionating column, and that causes all kinds of messes, and we don't need that. So basically, let's just put some boiling stones in there, and then we don't have to worry about it. Now, I'm kind of weaving here the experimental stuff in with the theoretical stuff. So you're going to have to pick that out when you're writing your hypothesis, to make sure you're focusing more on the theoretical stuff than the experimental procedure stuff. But one thing that's important for the experimental procedure stuff and the theoretical stuff is Le Chatelier's principle. So Le Chatelier's principle in this case applies because we have a reversible reaction. And if you'll remember, Le Chatelier's principle is that if we stress the equilibrium, the reaction will shift to respond to that stress. So in this case, the cyclohexene has a much lower boiling point than the cyclohexanol. And the reason for that is this has hydrogen bonding and this does not. So because of that, the fact that this doesn't have hydrogen bonding, it has a much lower boiling point. So what we want to do is we want to use a distillation apparatus so that we can remove the cyclohexene. In fact, what we're collecting in the receiving flask is cyclohexene. In a minute, I'm going to talk about how it's an azeotrope, which you don't really need to understand. But effectively, you're collecting the cyclohexene over here in your receiving flask. Well, if your cyclohexene goes over to the receiving flask, it's no longer in the distilling flask or the reaction flask that you originally put it in. So you're originally going to have a 100 milliliter round bottom flask over here. If the cyclohexene isn't there, then how does the reaction respond to this change in equilibrium? If this isn't here, if this is constantly, the concentration of this is decreasing because it's going to the receiving flask, then the reaction is going to shift to form more products. In fact, that's exactly what we want to happen. We're going to use Le Chatelier's principle to drive this reaction towards the products by continually decreasing the concentration of the product and therefore causing the reaction to shift to the right and form more of the product. So that's why we're doing this in a distillation apparatus. Note that this does make the separation scheme a little bit confusing because now the separation is occurring while the reaction is occurring. So we do need an extra step, if you will, in the separation scheme, but I will go over that later. Now, there is one important practical note here about this being an azeotrope. An azeotrope essentially means that the cyclohexene and the water will co-distill. So they don't distill independently of each other. They distill at the same time. And this causes a significant drop in the boiling point. And this is known, empirically, experimentally. We know that the boiling point of this mixture of cyclohexene and water is going to be somewhere around 55 to 60 degrees, which is significantly lower than the boiling point of cyclohexene alone. So don't be shocked if you see 55 or 60 on your thermometer and you see dripping into your receiving flask. That is what we would expect. Now, in this case, the azeotrope causes a lowering of the boiling point. Sometimes it causes an increase in the boiling point, but in this case, it causes a lowering of the boiling point, most likely because of the not strong interactions between water and cyclohexene, right? This molecule is very nonpolar, this molecule is very polar, so they're not super interested in being next to each other, so therefore it causes a lowering of the boiling point. Again, you don't really need to know what an azeotrope is, you just need to know that this reaction mixture boils or will distill around 55 to 60 degrees Celsius. What you're going to do is you're going to gently heat this thing, you're going to have this all insulated, and you're going to continue to do the reaction until you've gotten about 10 to 15 milliliters of the product in your receiving flask. Note that you may observe a large drop in temperature, okay? If your thermometer is reading 55 to 60 and then it starts to go down, that's a very strong indication that you are no longer distilling product and therefore you should stop the procedure, okay? Then what you're going to do is you're going to work up this reaction mixture and you're going to isolate it using a liquid-liquid extraction. You all are experts at liquid-liquid extraction, so I have no doubt you're not going to have any problems with this step. So what you're going to do is you're going to pour this receiving flask into a separatory funnel. Again, remember that when this distillation apparatus is hot, you are not taking off this distilling flask. It can cause flash boiling, it can cause dangerous things to happen, and it's not good technique. So do not remove this end. You can remove this end, then let this cool down before you take it apart. Okay, so you're going to take this, the receiving flask, you're going to pour it into a separatory funnel. You're going to use a little bit of water and then pour that into the separatory funnel. You're then going to use two 10 milliliter portions of 5% sodium bicarbonate. That is to remove any sulfuric acid. Now, sulfuric acid has a very high boiling point and is very unlikely to make it into your receiving flask, but we're going to use a lot of caution here and we're going to make sure that we get any sulfuric acid out of our product before we shoot it into the GC. So we're going to use sodium bicarbonate even if we don't necessarily need to. Now, just be careful because if for some reason somebody accidentally got some sulfuric acid in here, you can get a lot of bubbling. So you want to vent your separatory funnel often. And if you see a lot of bubbles when you add your sodium bicarbonate, you do not want to close it, okay, until you've gotten managed those bubbles, because you can have a pressure problem, right? The carbon dioxide can build up, just like in the acid-base extraction labs. After you use the sodium bicarbonate twice and keeping the organic layer both times, you're going to dry the organic layer with sodium sulfate as per usual. All right, you're going to use the solid drying agent. You guys know how to do that. And then you're going to move on to the product characterization step. You're going to take a 50 milliliter clean Erlenmeyer flask. You're going to weigh it. You're then going to pour your product into that Erlenmeyer flask and determine the mass of the product and the percentage yield. Then you're going to use GC to characterize your product finally by using 1 to 2 drops of your cyclohexene product in a vial full of acetone, and then you're going to inject into the GC. The cyclohexene should be showing up first because it has a lower boiling point than the cyclohexanol, but you're going to see if you have 1 or 2 peaks. Katie will have a standard available for you on the outside of the GC, so you'll be able to see the retention times of your product and of the cyclohexanol, and be able to know which you have. If you have both, I would anticipate that many of you, or most of you, should only see the cyclohexene product here. You should not see a lot of cyclohexanol, just because we're doing this reaction in a distillation apparatus, which should prevent the product from being ever over here in the first place. Said another way, we should separate the product from the starting materials before we even start the liquid-liquid extraction. So this is basically what you're doing in the lab. So I know I've been rambling on here for about 10 minutes, and I've given you lots of details, but I hope this gives you a good idea of what you're doing in this lab. What I'm going to do now is I'm going to go over the finding the limiting reagent and the theoretical yield, and the mechanism of the reaction, as well as the separation scheme. I'm leaving you a little bit on your own here to distill what I said down into a good hypothesis. Remember that your hypothesis should not focus on the experimental details, but it should focus more on the general principles of, for example, why we're using distillation, how much product we're going to isolate, how Le Chatelier's principle plays a role, how sulfuric acid is a catalyst, and so on and so forth. Thanks for watching this section, and I'm going to stop here and then move on to the next part. So in this part of the video, I'm going to go over the limiting reagent and theoretical yield. So in this case, you only have one reactant, so this has to be the limiting reagent. So we were going to add 10 milliliters of cyclohexanol, and we're going to add 6 milliliters of 7.5 molar sulfuric acid. But again, this is a catalyst, so it's reformed during the process of the reaction. So this never gets used up. So this has to be the limiting reagent. Note that cyclohexanol is very viscous, which means it's thick and syrupy. So if you try to transfer this by a transfer pipette, it will take forever. So it's going to be really important that you pour your 10 milliliters of cyclohexanol into the graduated cylinder, and not try to transfer it by a transfer pipette. It's also important that because as you're going to see, it turns out that if you're going to use 10 milliliters of this, because of the change in density, so you have a change in molar mass, but you also have a change in density, you actually end up with about 10 milliliters of this. So make sure you're not distilling to dryness, okay? So don't try to get 15 milliliters of this pushed over, because this can't be dry. So don't distill to dryness. That's really important, because then you're going to potentially get some of this in your product mixture. So wait for that temperature drop, or that kind of thing, so you're not distilling to dryness. All right, so since we're using a 10 milliliters of this, we actually need to know the density. And if you look up the density, it's 0.962 grams per milliliter for cyclohexanol. So we need to convert the milliliters to grams. All right, so we need to convert the milliliters of the, I'm going to call it C-hexol. All right, just so I'm abbreviating it. We want to convert that to grams of C-hexol. All right, once we have grams of C-hexol, we can convert to moles of C-hexol using the molar mass. Again, that's just an abbreviation. Then we can go to moles of C-hexene. And then finally to grams of C-hexene. So it is a very, very long conversion process here, but we have all the stuff that we need to be able to do this. So in order to do this reactions, we are going to need the molar mass, and it turns out that the molar mass of this one is 100.16 grams per mole, and the molar mass of this one is 82.14 grams per mole. So now we have just to do this conversion. So starting with milliliters, I'm going to do 10.0 milliliters, so that way I can have 3 sig figs in my answer, and a graduated cylinder can certainly get 10.0 milliliters. So for every 1 milliliter, we're going to have 0.962 grams of Cyclohexanol as the abbreviation. Why? Because it's 0.962 grams per milliliter. So every 1 milliliter has 0.962 grams. We now want to convert to moles using the molar mass. So if we have grams here, we want to put the molar mass on the bottom. In this case, the 100.16 grams of the Cyclohexanol per mole of the cyclohexanol. All right. Now we want to go from moles of cyclohexanol to moles of cyclohexene. That's the balanced chemical equation, and we have one of these forms one of these. So every 1 mole of cyclohexanol forms 1 mole of the cyclohexene. All right. Finally, we want to convert from moles of cyclohexene to grams of cyclohexene. So in this case, we put the 1 mole of cyclohexene on the bottom. Can't even remember my own abbreviations here. And then the 82.14 grams of the cyclohexene on the top. And when you do all that math, you get 7.89 grams of the cyclohexene as the theoretical yield of your product. Note that because this is significantly less dense, this has a density of around 0.82 as opposed to 0.96, the volume turns out to be around 10 milliliters as well. So this is how we calculate the theoretical yield, which you need for your lab report. So in this section, my plan is to go over the reaction mechanism. So this is occurring by an elimination reaction, and it turns out that it's an E1 reaction because we're going to have a secondary carbocation that is formed. So let's take a look at this mechanism. When you're doing your mechanism discussions, it's a good idea to point out what is the electrophile and what is the nucleophile, because when you do that, it shows clear understanding of what's going on. So in this case, what we have is a little different than an elimination of, for example, an alkyl halide, which you may have covered from the lecture course. But in this case, we have an alcohol. So the OH is not a very good leaving group, but it does have 2 lone pairs on it. And the reason the OH is not a very good leaving group is because it's a pretty strong base. So what we need to do is we need to first protonate the alcohol in order to make the leaving group leave. So to do that, the lone pair of the alcohol takes the proton. Okay. This means that this lone pair acts as a nucleophile, or oxygen acts as a nucleophile, and the hydrogen, the H+, acts as an electrophile. So the nucleophile attacks the electrophile in this way, and what we end up with is a ring, okay, and this ring now contains an O, now with just 1 lone pair, and 2 H's. It is essential that you can calculate formal charges very quickly. An oxygen with 3 bonds and a lone pair is always plus. But how do you know that? Oxygen wants to have 6 valence electrons, and formally, 1 of each of the electrons in this bond and both of the electrons in the double bond are for oxygen. So you count the dots as 1 and dashes as 1. So this has 1, 2, 3, 4, 5 electrons around it. Oxygen wants to have 6 electrons around it. It's missing an electron, so it's plus. Again, oxygen with 3 bonds and a lone pair is always plus. It's hard to learn patterns. You learn rules, and then you see patterns. All right, so now we have this. Now, if you notice here, we have water. Water is a good leaving group. Because this is an E1 mechanism, because we can form a secondary carbocation here, this water is just going to leave. So just like that. And what we end up with, these are all these steps are reversible. So I guess I should write it like this, okay? Because we end up with this leaving group here, what we end up with is the ring and a positive charge, all right, plus H2O. all right, the leaving group. Now, the elimination occurs because you have hydrogens on these adjacent carbons. All right, there's two hydrogens here, and there's two hydrogens right there, like that. Now, I haven't been showing these before because they're implied, but because carbon has 4 bonds, it must have two hydrogens here. If you look at this carbon, it has 2 bonds to carbon, and now 2 bonds to hydrogen. We need to eliminate one of these. Now, if we were using if we had a difference, so for example, if we had a methyl group here, then a methyl group on this one and no methyl group on this one, it would prefer to eliminate this because then we'd end up with the more substituted product. In this case, we have symmetry, okay? So we don't need to worry about Zaitsev's rule of forming the more substituted product because in either case, all right, if we eliminate one of these hydrogens or we eliminate one of these hydrogens, we're going to end up with a double bond here or a double bond here. And in both cases, that carbons in the double bond are going to be bonded to one carbon and one hydrogen each. So it's the same. We have symmetry, however you want to say it. So the water molecule can act as a base here, or we could say another way, the water molecule acts as a nucleophile. Okay, so this water molecule is acting as a nucleophile and grabbing this H+. The H+ is acting as an electrophile and interacting with the lone pair on the water. And then these two electrons in this bond shift into a double bond. And what we end up with is this, where this has been eliminated. We have the one H that's already drawn. It was kind of drawn over this way, like this. And we reform the catalyst by forming H3O plus, because now this has 3 H's instead of 2, and it has the positive charge from the H, and that's your acid-base chemistry. So this is the elimination mechanism. Again, we don't need to worry about Zaitsev's rule, which is saying that we'll form the more substituted alkene, because in this case, we don't have a difference, right? It's symmetrical, but that does come up on the post-lab questions. We'll also note that this is an E1 mechanism. Why is it an E1 mechanism? It's an E1 mechanism because the water leaves forming the carbocation. So the rate of the reaction is based on the slow step, which is the formation of the carbocation. So this step right here is the slow step. It only forms on matters how fast water leaves. There is no pulling of a proton off causing the water to leave here because it's an E1 mechanism and not an E2 mechanism. So hopefully that gives you some idea of how this mechanism proceeds. All right, so in the last step of this video, I want to look at the separation scheme. And the separation scheme is a little different for this one because the reaction and the separation are kind of occurring at the same time because we're reacting here and we're distilling at the same time. So the first separation is the distillation, which is a little different than the previous reaction, and it's actually a little different than any of the other reactions we do in organic chemistry. So I do want to spend a little bit of time going over it. So we can consider, because it's the original reaction, that what we are starting with is the cyclohexanol. Make sure you can see that, all right? The sulfuric acid, okay? Because those are what we started to mix together. But we can also assume that we have the cyclohexene and the water as well. All right. Now, we add water because this is 7.5 molar sulfuric acid, so we have water because of that, but we also have water as a product of the reaction. And then the first thing we're going to do here is we're going to distill this mixture. And we're going to have 2 flasks in the distillation. We're going to have the distilling flask, which is this one, and we're going to have the receiving flask, which is this one. So what's going to be in our distilling flask? Well, what should mostly be in our distilling flask is any unreacted cyclohexanol, as well as the sulfuric acid, which again is fairly unlikely to go to the receiving flask simply because it has a very, very high boiling point. And we should also have the water. Now, theoretically, all of the cyclohexene should move to the receiving flask. Is that to say there's not one single molecule of it that didn't make it all the way through this fractionating column? Probably not. So if someone were to put here trace cyclohexene, they probably wouldn't be wrong. So these are not a thing where there's like, they're black and white and there's a right answer and a wrong answer. I'm going to leave it off over here, but it's not terribly wrong if somebody puts it over here. The receiving flask should mostly contain your cyclohexene, okay, because we're going to push it over into the receiving flask. But it's also going to contain water because this is an azeotrope, so it's definitely going to contain water. That's why the boiling point is so low, 55 to 60 degrees C. And it may contain, although unlikely, trace sulfuric acid. But we're all going to assume that it does contain sulfuric acid, and be careful in the next step of the separation, because again, if you add the sodium bicarbonate to sulfuric acid, you can get a lot of CO2, so you need to vent. You need to make sure before you even put the cap on, that you aren't generating large amounts of CO2, because that can build pressure and be dangerous. All right, so now we're going to do the next step, which is 2 portions of 5% sodium bicarbonate, NaHCO3. Okay, now we're going to have the 2 layers. In this case, we're going to have the aqueous layer and the organic layer. Now, the organic layer, all right, is your cyclohexene, right? That's the main organic layer. So it acts as both the solvent, if you will, and the product, all right, because this is what you're mostly going to have. Now, in your aqueous layer, you may have some sodium sulfate if you had any unreacted sulfuric acid. It will be converted to sodium sulfate. Sodium sulfate is ionic, and it will not go into the organic layer. If you did have some of this, okay, you're certainly going to have water. That's redundant for the aqueous layer. That could be there or not. You may have carbon dioxide bubbling out, okay, of the solution if there were some sulfuric acid. Again, do you need these here? Maybe, maybe not. There's not one right answer here. So that's, basically that. Now over here you have the cyclohexene, but because you did a liquid-liquid extraction, you certainly have traces of water in your product. Okay. Finally, what you're going to do is dry this with your anhydrous Na2SO4, your drying agent, your anhydrous sodium sulfate. You're going to have a solid, which is Na2SO4, and some number of water molecules. I'm going to put X water molecules coordinated to it. Sorry, you can't see that. Okay. And then over here, you should have your nice dry cyclohexene. Now, we don't need it in the separation scheme, but the next thing you're going to do is you're going to take a couple, you're going to find the mass of this product by taking a clean and dry 50 milliliter Erlenmeyer flask. Take its mass, then fill it with your product, and then take the mass again to find the mass of your product. And then you're going to take a couple drops of it, put it in some acetone in a GC vial, and shoot it into the GC. Again, in the GC, the cyclohexene should come out before the cyclohexanol, and Katie should have a spectrum available by the instrument so you can see the retention times of both of those things and see how your reaction went. Again, this is a little bit different of a separation scheme. There are several parts here where it's questionable whether you're going to have any sodium sulfate here or not, because, if you didn't have any sulfuric acid, you're not going to make any sodium sulfate. So there are several examples as I went through it. So this is one answer. It's not the only answer. I know that causes confusion because people like there to only be one right answer, but unfortunately in life, that's rarely the case. All right, thanks for watching this video. I hope you found it helpful, and we hope you enjoyed this lab. This is a good, synthetic organic chemistry type of reaction. Thanks for watching.